serial where you can easily find your voltage and your ground, and then your TX and your RX pins. With this, you've got to get the 4 input pins correct to find the correct output pin, which is the response pin. So if it weren't a standard, it would be very difficult to figure it out on your own.
Don't skip yet. While they're not standardized terribly well among between manufacturers, usually one manufacturer will use the same JTAG pinout on all their boards. The router that we've been showing off and another router that I have both use MIPS processor cores, and their JTAG headers are both MIPS JTAG standard. The other lines here, TDI, TMS, T-Clock, and TDO, are the actual lines used for doing the JTAG communication. TDI is test data in and is a single wire serial line that's used to send data into the chip. TMS is test mode select, which is basically the enable for doing JTAG stuff and tells the test section of the chip to enable itself. T-clock is the clock signal, which is used for clocking the data in on TDI and out on TDO. So the way it's used is that data is sent into the chips, and then the resulting data is clocked back out. Because, if you'll skip to the next slide, this is a example layout of a set of just an arbitrary device that supports JTAG. The individual devices are daisy-chained, TDO to TDI, and they all share one T-clock line. So the data can be clocked into one device, and then if you want to reach the next device, you just keep clocking it, and it goes into that device, and then into the last device, and then finally starts coming back out on your TDO line. This is essentially a shift register, if anybody knows what that is, that incorporates every pin of every device in the circuit. This means you can set, under software control, the state of any device, or the state of any pin of any device in the circuit. So you can do what-if scenarios where you can say, well, what if all the data lines went high at once? You just clock in a whole bunch of ones until they're at those data lines and then see what happens. Another use is getting flash in or out. Since the flash chip will be connected to something that has JTAG pins, JTAG can be used to manipulate the pins that are connected to the flash chip, changing its address and address lines and then reading its data lines back out through the TDO port. Needless to say, this gets somewhat tedious. It's a single-bit serial protocol, and if you're trying to read several megs of flash over it, it can take a very long time, sometimes up to a half hour for reasonably sized flash chips.
There are open source tools available that will allow you to do manipulation via JTAG port. Depending on what device, there might be specific tools like routers have their own. I think there's one called Harry Dairy Made, yes, which is for debricking a router via JTAG port, and it's a very primitive implementation of the JTAG, but it does what it's intended to do.
EPROMs are a technology for storing data on circuit boards that came well before Flash. You've probably seen an EPROM chip if you opened up any older devices. They're usually kind of large, wide-bodied, and they usually have a clear window on the top that you can see the chip through. The reason for that is that the chip, it used to be that you would program this chip in a device called an EPROM burner, and then take it out, put it into the device, test the device, and if there were any problems, you could then take it back out and erase it using ultraviolet light through the window on the top, and then put it back in. This is a hobbyist's homemade EPROM reader and writer. They're useful if you have an older device, and in my case I had the magnetic card reader that I was talking about, to be able to dump all the code out of one of these EPROMs. If you have an EPROM that you can get the code out of, and you know the microcontroller that was used for it, you can use a program like IDA to reverse engineer the software, and from that modify or just even come to a basic understanding of the device. Do-it-yourself ones are available. This is kind of complicated, but if you look at these chips, they're all very basic logic chips. This is designed to be driven off of the parallel port of a standard PC using some Linux-based software, and would probably cost well under $100, possibly under $50 to put together. The thing is, EPROMs are fast disappearing. They're an older technology, they're less easy to work with than Flash, and possibly less reliable. They also come in smaller sizes. Flash has kind of replaced them, and if you want to dump flash memory, you might do something like this. This device here is a digital camera made by a company called, I believe, Dakota Digital, that was sold as a disposable video camera at pharmacies in the United States. People didn't want to return it, though. They wanted to be able to buy one, use it to record videos, and then offload those videos onto their computer and record more videos, instead of sending it back to the company to be processed and receiving the videos later and never getting their camera back. I mean, it's a simple money-saving thing. You don't want to buy a camera over and over and over again just to record short little videos.
And because you only rent the equipment, you're only paying $10 for a camera that might be worth 40 or 50 bucks.
So perhaps not in the
retail.
company's best interest, but certainly in the people's best interest. The device that's clipped onto it is a reader for XD or smart cards. XD cards, which are used in Olympus digital cameras, and smart media cards, which are used in some other companies' digital cameras, are basically a typical flash chip in a funny-shaped package. They have all the same data lines, all the same address lines, same power and grounding, and just this exact same signal set, just in a different package. This device is an adapter between a USB connection and the flash chip on this board. So the person can connect this up and then mount the flash chip as if it were a drive on their computer, use a program like DD or Copy to copy the data right off of there and into a file for later analysis. People did this and managed to reverse engineer out of it the unique keys that were used to, I believe it was either encrypt the data on the card or to authenticate to the camera before downloading the data out of it, and then could connect basically a USB port to these traces over here and get the data out themselves at home. The other possibility for getting the flash out is desoldering the flash chip, which is doable if you have hot air stuff, but is not a terribly easy process.
Once you get the firmware off and have it decompiled, you're going to have a big blob of assembly instructions, pre-initialized data for when the program starts off, and typical tasks it's going to do is it's going to do on the system on a chip initialization. It's going to initialize all its subsystems, set its memory registers, map the memory, and then it's going to clear the RAM, copy the initialized data into RAM, and start the main loop after creating the stack. So the first thing you want to look for is the reset vector of your chip, because that's your start point. Another nice thing is interrupt tables are usually well documented, and you may have 100 bytes per interrupt to have the interrupt inline, or most places will just branch off to a larger area of memory to do each interrupt routine. So you'll have like a serial interrupt, an SPI interrupt, basically interrupts for whatever timers and everything else on the board. And knowing that will tell you where to start, and once you start tracing through, you can start documenting this decompiled assembly code when you figure out what it does.
Once you have the software, it becomes a matter of software reverse engineering. You end up, like he says, tracing the interrupt vector to find your entry point and then decompiling the code. The difference is that you may have to learn the assembly language, the processor register layout, and the memory map of a whole new processor, because the chip isn't necessarily going to be the x86 that the average program runs on. However, most manufacturers want it to be easy for you to learn their assembly language, their register maps, their memory maps, because they want you to use their chip. So if you get the data sheet for a chip, you can probably teach yourself the assembly language just based on that. The magnetic card writer that I dismantled and reverse engineered used the Motorola 6803 microcontroller. The Motorola 6803 microcontroller datasheet has a full table of what every single assembly language instruction does, memory map, where the interrupt reset vectors are, what the registers are, how the commands interact with the registers, everything you could want to know about programming the chip. and as a consequence, everything that you would want to know about taking the program out of the chip. What in the world is... It's a parade! Yay!
Just wait for a second for that to get by. It's a little distracting.
Well, that was really something. Once you have the data sheet, you can teach yourself the assembly language. And once you learn one assembly language, the majority of assembly languages are, to some degree, similar. You'll end up with, you know, the typical push, pop instructions. In Motorola assembly language, interestingly enough, the pop instruction is not pop, it's pull. The opposite of pushing something onto the stack would obviously be pulling it off, not popping it off, which is an interesting piece of design decision on their part. Go ahead.
This slide also got screwed up a little bit. I'm not sure quite what happened.
We have a variety of people we'd like to thank. We'd like to thank the Hacker Foundation for putting together our trip over here. We'd like to thank the CCC for having us and the Angels for making our stay here easy. We'd like to thank all of you for coming to this presentation.
We're also thanking the Hacker Foundation, and they're trying to start the Hackerspaces program in the U.S., which is encouraging people to group together, to work together on creating their own labs and pursuing their own projects. We wouldn't have been able to do this talk without collaborating and sharing knowledge, because he knows many things I don't know and vice versa. So if we weren't working together, there's no way either of us would have been able to put together this talk at the quality that we've made it. Here in Germany, you've got the CCC, which is very graciously hosting us and allowing us to speak. It's an excellent organization which encourages stuff like this. So thank you, and I guess now we're going to unplug the laptop and plug in the monitor for questions.
Yep.
Now, before you run off to your tent and fire up your soldering iron, there's a lot of time for questions. Are there any questions?
Just a very basic question about soldering. What's the right temperature for soldering? Because it always seems like a religious belief.
Well, on the topic of religious belief, I typically keep my soldering iron set at 666 degrees. That works well for me. I have yet to burn anything out.
For sensitive electronics, a range between 600 to almost up to 800, maybe 750 or so, can safely be used. You might want to go higher if you're desoldering, because that generally goes faster if you're using a wick to pull the solder out.
Yep. Yes, I believe
Fahrenheit.
it is.
Yes.
Yeah. Yep, Fahrenheit. Anyone else? Another thing, you can look up the data sheets not only on chips but on solder as well. There's low temperature solders, there are higher temperature solders. Basically, you can bring it down to trial and error. One thing that is good to have, though, is a temperature controlled iron. Very basic soldering irons are not temperature controlled. They just limit how much current passes through the device, which doesn't adequately regulate the temperature. It means that when you touch it to something that's large and can sink a lot of heat away, the iron temperature will plummet. And it may take a long time to heat the thing up. It may end up applying too much heat to the area under the iron before anything else is hot enough to solder to. If you have a temperature-controlled iron, it will detect the drop in temperature caused by touching something like that and send more power. I use a temperature-controlled iron. I grew up using a non-temperature-controlled iron, and the difference is, frankly, fantastic.
Yeah, my soldering iron has two settings, 20 watts and 40 watts. I use 20 watts for applying most components to the board, and 40 watts for desoldering from the board. But if I'm trying to solder something to a grounding plane that's